in chapter 12, we've been focusing on just the regular kinematics motion. And just like we did in that first physics class, you went from kinematics, those equations of motion without regard for what was happening in the motion. We didn't necessarily know why the car was traveling down the road. We didn't necessarily know how that was all working, but we're now moving into that why portion, and we're bringing in our force and acceleration. So we're doing chapter 13. We're getting that start in chapter 13. So remember, in statics, we focused on systems that were not in motion. All right, we focused on systems that were in equilibrium. And we essentially only had two rules, and these rules were related to that static equilibrium: our summation of forces and our summation of torques. And remember, those summation of forces, if we were in statics, that was equal to 0, and our summation of torques, if we were looking in statics, that was equal to 0. So recall that motion is the result of an unequal force. Think of a tug of war. So I've got a little simulation here that we can actually do and actually see. If I've got tug of war, we have 150 newtons pointing to the right, we have 100 newtons pointing to the left, and we know that ultimately the cart is going to move towards the right because there's an unequal amount of force being applied, and when we do the addition of those forces, we get a 50 Newton force resulting in motion to the right. So that tug of war, we get a flag, a cart, whatever. We think of the direction of the greatest force, and the net force results in the addition from the addition of the two forces. Also recall that mass is a ratio. It's a ratio of the force to the acceleration, and we can consider that a resistance to motion. The greater the mass, the greater the force that must be applied in order to get the object to change its motion. Remember, we have those other two Newton's laws. This is a representation of Newton's second law, but we also have the law that says for every reaction, there's going to be a reaction, and an object in motion remains in motion unless it's acted upon by another force. It's traveling at a constant velocity. It's not going to change its velocity unless we've got a force there. And most of the time in statics, we said that velocity was equal to 0. So in other words, the mass is a quantitative measure of the resistance of the particle to change its velocity. Remember, we define that as inertia. So let's go back and let's look at a little bit of things about gravitation and gravitational force. As we've seen before, it doesn't matter what the object is, it's going to be impacted by gravity, right? So we've got a ball, an acorn, an anchor, a feather, anything, it's going to be acted on by gravity. The shape's not going to change how gravity is going to act on that object, because remember, we're talking about the thing is going to act like a particle, and it's going to act through its center of mass. So we're not going to see anything that's there, but the overall motion is going to be impacted by the other forces. So if I'm in a vacuum, the ball, the acorn, and the anchor are all going to take the same amount of time to fall. We might see a change like with the feather or a parachute because we have other forces that are acting on it. We have that force due to drag. Okay, remember the bowling ball feather video where if I had drag due to air, the feather is going to behave a little differently than the bowling ball, but if we were in a vacuum, the bowling ball and the feather are going to hit the ground at the same time. So when we're dealing with this part, and the reason we bring that up is because remember that weight and mass are two different things. Weight is related to that action due to gravity. Mass is related back to inertia. So any two particles have a mutually attractive gravitational force. Remember Newton's law of universal gravitation. And near the surface of the Earth, we can talk about that as being weight. If we're on the moon, we can talk about it being weight associated with the acceleration due to gravity on the moon. If we're on Jupiter, with anything like that, we can look at what's happening near the surface, and we can look at it. And so the weight of the body can be simplified as the mass times that action of that gravitation. And just remember that if I'm doing Newton's law of universal gravitation, F is the force of the attraction between the two bodies, G is the universal gravitational constant, M1 and M2 are the mass of each body, and R is the distance between those points. And also recall that when we start dealing with it and expanding on it, we get that center of mass. So let's look a little bit more. So remember that we're going to be dealing with both common units and SI units. So our acceleration due to gravity is 9.18 meters per second squared. If I'm dealing with the common English units, it's 32.2 feet per second squared. And the motion on the Earth's surface, as we talk about it, and as we've seen over and over and over again, that we can rewrite Newton's second law as the summation of forces is equal to mass times the acceleration. And that's going to end up in a resultant force. Remember, these are vector quantities, so that we have to keep account of our vectors. And that's what we have in this case. But I want to point out that this equation of motion is only valid if the acceleration is measured in a Newtonian or in an inertial frame of reference. All right? This is only valid in a Newtonian or an inertial frame of reference. And that's really important to think about, because we always talk about this summation of mass times acceleration, but if I'm dealing with other frames of reference, I may not be able to use this equation. It's a special case, and we know we're going to have to draw our free body diagrams. So let's take it a step further. That inertial frame of reference deals with my force due to gravity, and applying when F is equal to ma. The acceleration of the particle is measured with respect to the reference frame that is either fixed or translates with a constant velocity. That's why if I'm dealing with it on the surface of the Earth, I'm fixed with the spin of the Earth. I don't have to account for the rotation of the Earth, because we're in a fixed, or we're translating with that constant rotation of the Earth velocity. So for problems concerned with motions at or near the Earth's surface, we are fixed to the Earth, and we don't have to do that effect of the Earth rotation. For problems involving satellites or rockets, the inertial frame of reference is often fixed to the stars. So when we talk about orbital motion, or we're talking about other motion out there, we probably are going to have to pick a reference point in order to really understand what's happening. So we need to have that inertial frame of reference. So we also look at it in terms of a system of particles. Remember, we can look at a big object as individual objects. So the equation of motion can be extended to include systems of particles, includes motions of solids, liquids, or gases. But in that case, we're going to have to sum up this, each individual mass components. Remember, that's why we want to do integrals, because that helps us solve over our object. The internal force F is a resultant of all the forces that are exerted on the ith particle as a sum of all the other particles. And we can look at these individual sums, and we can come back to F, or m times my gravity, is the sum of all of those. And it gets us back to that initial result in terms of our center of gravity. So you can go back and look at all of this, because it all comes back to even a big object is going to act like it's a particle, depending on how I'm designing my equation. So the sum of the forces is equal to mass times our acceleration due to gravity, and it's going to act at the center of gravity. And we also know that acceleration has an x component, a y component, and a z component. And we end up with our three equations for our forces in the x, y, and z, because we have that independent equation. Just like what we were seeing in statics, except now instead of these things ending up being equal to 0, you've got a chance to see the motion in those different directions. So some key points. Newton's second law is a law of nature. It's experimentally proven, and it is not the result of an analytical proof. Mother Nature's there. It's one of those laws. The mass of a object is the measure of the resistance to the change in velocity. Weight is related back to the force dealing with gravity. Unbalanced forces are what's going to cause us the acceleration of the objects, and this condition is fundamental to all our dynamics problems, because in statics, we made sure that the forces did balance, and in dynamics, the forces do not have to balance. So now we have a procedure for how we're going to deal with these problems. You want to select a convenient inertial coordinate system. You want to make sure you draw your free body diagrams. You want to draw the kinetic diagram. So we're going to add things like friction. We're going to add things like velocity. We're going to add other components to it. So those free body diagrams that we've spent so much time on become incredibly important here. Then we apply our equations of motion on their scalar components, solve them, and we may have to apply proper kinematic relationships. So to help us with this, we've got a couple of examples. So let's start with this one. We're given a 10-pound block, and we have a force that's being applied as a function of time, as shown on the block. We do have a force due to friction, and we want to find the velocity after the block has traveled 30 feet, but we do have an initial velocity. So first thing we'll want to do is we want to calculate the magnitude of the force. So I'm going to use the friction as fun. And we know that we've got 10 pounds, so my force due to friction is a 2-pound resistive force. So the summation of forces, because I'm only in the x direction here, the summation of forces in the x direction is going to be the mass times the acceleration. Our acceleration is going to be in the x direction, and it's going to have an equation that looks like that. We also have our kinematics equations. So we want to know the velocity after it travels with a change in 30 feet. So this is going to be the equation that we want. But I also can deal with my integration. So let's start with this one here. I've got the integral over velocity, and I've got my acceleration times time. And I can go from 4 feet to my final. And I have this component here because I need my mass, right? I'm going to divide this side by the mass. And this comes from finding the mass in slugs. So I have to account for gravity. And I've got my integral with respect to time. So we go ahead and do this, and we're going to evaluate from 0 to t. We go ahead and calculate it out. I get a new velocity with respect to time. I can do the same thing with my distance with respect to velocity. So I'm going to plug this one in there, and I can get all the way down. And the thing is, we didn't know t, which is why we couldn't just directly pop it into that equation. So now I can go in here and find my change of distance, and we have a bit of differentiation. So we can go through this. And ultimately, we're going to have to solve this one numerically. So go back to your calculus book to look at how you can solve that numerically. And we find that at t is equal to 0.0089 seconds, the velocity is going to be 60.7 feet. And we can go in and work that type of problem. So let's look at another one. This one happens to be problem 13-8. And in this case, we want to find the velocity when it reaches this point. So I've got two components here. I have a component in the x direction. I have a component in the y direction. And we know that our sum of the forces is in the parallel direction. Parallel to this is going to give me my acceleration coming off at the end. And we can work through this problem just like our standard type of a problem. And then finally, I've got another one that looks an awful lot like the penguin problem that we've done in the past. We want to determine the shortest time for the truck to reach a speed of 60 kilometers per hour, so that the box does not slip off the back. We're told that the mass of the box is 200 kilograms. Its static friction is 0.3, and we can do the normal force. We have to calculate our normal force in newtons. We know that if the force exceeds our 588.6 newtons, it's going to slip. So we know we can go in there and we can find the acceleration, and then we can back find the time. Hopefully that gets you started, and we'll continue to work some other examples.